In this video, we are going to discuss how to derive an expression for magnetic flux through a rectangular loop due to a long straight wire carrying current. So in this question, you have a straight long wire that lies along the y-axis and carries a current I as shown below. A rectangular loop of dimension 6 meter by 4 meter is located 1 meter from the wire. The current in the wire varies according to I equals 3.01 minus beta t, where the value of beta is 0.12 ampere per second. We need to derive an expression for magnetic flux through the rectangular loop of wire. So here we have a current I going through the straight wire, which is a function of time given as 3, 1 minus beta t. And I need to find an expression for magnetic flux on the rectangular loop because of the wire. We know that magnetic flux phi is given as P A cosine theta. Here the magnetic field is due to the straight wire, so I will write magnetic field of wire. And we are finding the flux through the loop, so it will be the area of the loop. And theta is the angle between them. Now for a straight current carrying wire, magnetic field lines are in the form of concentric circular loops. And you can find the direction of this magnetic field by using right hand rule. So if you point the thumb of your right hand in the direction of current, your fingers will curl counterclockwise, and therefore the direction of magnetic field is also counterclockwise. And through the loop, magnetic field lines, if you draw a tangent here, will go into the loop. So I can show direction of magnetic field due to the straight wire going into the loop. Into the loop you represent by cross. So these are the direction of my magnetic field lines through the loop. Then area vector we always take perpendicular to the plane of the loop. And since this is an open loop, I can take the area vector either coming out of the plane or going into the plane. Since the magnetic field is going into the plane, I will take the area vector in the same direction. Now I can only do this when the loop is open. If there was a solid plate here or a closed surface, area vector through such surface always have to point out of the surface. Now taking these directions, I get the angle between magnetic field and area vector to be 0. And we know cosine 0 is 1, so I can get the flux as just product of magnetic field with the area. Now magnetic field due to a straight wire is given as P equals mu 0 I over 2 pi r. Looking at the expression, we get that magnetic field B is inversely proportional to the distance from the wire. That means as I go away from the wire, the value of magnetic field decreases. So since the different points on the loop are at different distance from the wire, the value of magnetic field will vary. It will not be the same at all points. And if magnetic field is not same, magnetic flux will also change. So magnetic flux at different points on the loop will be different, and we need to take that change into consideration while writing the value for flux. So instead of writing the flux as B into A, I'm going to take a differential value of flux and write it as d phi, which will be dB into A. Now this is differential value because the value of magnetic flux is changing. So I can calculate a differential value of magnetic flux at a specific point and then integrate that value to get the total value of flux. We already know the value for magnetic field. Area of rectangular loop can be written as length times the width. Let this be the width of the rectangular loop and this be the length. Length I will call as A. So this becomes equal to A times W. But the length lies on the axis, which gives you the distance of the loop from the wire. And this is the distance that is changing and causing a change in the magnetic flux. So when I'm finding differential flux, I have to take the differential value of this distance. So when I'm solving for differential area, I have to take differential value of this distance from the wire. So I'm going to write this as W times dr. Now why did I write dr instead of writing dA? A is the length of the loop. But when we are calculating the magnetic field, we take r to be the distance of the point from the wire. And this is why when I'm solving for differential area, I will take this distance to be dr in place of a. And while solving using integral, I will put the limits in terms of a. So we rewrite this as mu 0 I over 2 pi r into w times dr. This is my differential flux. I will integrate this flux to find the total value. So we get phi to be equal to integral mu 0 I over 2 pi r into w times dr. We are integrating this value over the length of the loop. So the loop begins at this point on the x-axis, let us call it d, and it ends over here after a distance a. So this point on the axis will be d plus a. So we will integrate from d to d plus a. As shown in the figure, d is 1 meter from the wire. Length of the loop is 6 meter. So d plus a will become 1 plus 6, which is 7 meter. Now let's rearrange this. Mu naught I over 2 pi is a constant. W is also a constant. We can take it out of the integral. So we get mu 0 I over 2 pi times W. Now I is changing with respect to time. It is a function of time. So it is not constant with respect to time. But we do not have to integrate I with respect to the distance r. This is why when I'm integrating with respect to distance, I take I out of the integral as it is a function of time, not distance. So here we integrate 1 over r dr over the limits of d to d plus a. So this gives me mu 0 I w over 2 pi. Integral 1 over r will give me len r. The limits will become from 1 to 7. Now let's solve. We get phi to be equal to mu naught I w over 2 pi. When you substitute the limits, you get upper limit minus the lower limit. So len 7 minus len 1. That becomes equal to mu naught I w over 2 pi. When you subtract two logarithmic value, it is equivalent to write it as len 7 over 1. Now substitute the values of mu naught I and w. Mu naught is 4 pi times 10 to the power negative 7. I is 3 times 1 minus beta t. W is 4 len 7 over 1 over 2 pi. And when you solve this, you get the value of phi to be equal to 4.67 times 10 to the power negative 6 into 1 minus beta t Tesla meter squared. So this is the expression of magnetic flux passing through the rectangular loop because of the straight wire carrying current. You can substitute the value of beta over here or just keep it as it is as they are asking you to find the expression. Now let's discuss the second part of the question. In the second part, they have given you the value of beta, which is 0.12 ampere per second. And we need to find the magnitude of induced EMF. Now, induced EMF is given as negative derivative of phi, which is equal to negative derivative of 4.67 times 10 to the power negative 6, 1 minus beta t. That gives you negative 4.67 times 10 to the power negative 6. Now this number here is a constant multiplied to the rest of the term, so we can take it outside of the derivative. Derivative of 1, which is a constant without t, will be 0, and derivative of minus beta t will just be minus beta. Now let's substitute to calculate V induced. Negative 4.67 times 10 to the power negative 6 minus beta is 0.12. That gives you induced EMF to be equal to 5.6 times 10 to the power negative 7 volt.